Here are solutions to test number 2 for ECE 463 Modern Control. Now, the goal of this homework is to take a gantry system like this. This is a mass that you're pushing on with a force. So here's your force. Attached to it is a pendulum. Get it to go from point A to point B without swinging too much. And just to make life hard, there's a disturbance, a force on it, pushing it right, and your set point is a sine wave. So what it should look like is something like this. I've got the set point going back and forth as 0.5 radian per second sine wave. I've got the cart going back and forth. It should track. So how do I do that? And it's kind of got three different versions. If I can measure all the states at the C level, if I can only measure position and angle at the B level, in which case I need a full order observer, and at the A level, can only measure position, angle, and you have a constant disturbance. So let's start out. In any of those cases, I need to come up with a controller. So to do that, I'll take the dynamics. Here's the system's A matrix. There's the B matrix. It changes each semester. For this semester, that's your A and B. Come up with a servo compensator so that I can track a sine wave and reject a constant. So to do that, input the dynamics into MATLAB, add a servo compensator. This servo compensator has poles at 0 and plus minus j.5. The union of the singularities of the disturbance and the set point. So there's many ways of doing this. This is one 3x3 matrix that has the 3 eigenvalues, so that's a valid one. The B matrix is anything that makes this controllable. So I just chose 1, 1, 1. Putting it all together, here's the plant plus the servo, and kind of what that looks like. Going back to the end. Don't need this initially. Got my plant, got the servo compensator, have full state feedback. This is feeding back X and servo. Find Kx and Kz. Well, what we're doing right now is pole placement. So once I form the augmented system, this is now a 7th order system. There's my 7 by 1 vector for B. Use pole placement. So let's just put the poles at minus 1, 2, 3, 4, 5, 6, 7. It's not really specified where you want to put the poles. It's just got to be stable. Well, that's actually not a very good idea, because if I do that, I get gains of 10,000. So that's going to cause trouble. Let's instead try a different pole location. Let's take the open loop poles and just shift them left by 0.5. So here's where I want to put the poles. Again, kind of arbitrary. The pole location is not specified on the test. If I choose this pole location, I get much better gains. That's actually much more reasonable. It's not 10,000. Biggest gain is 14. So let's go with that. When I do that, the first 4 states were X. The last 4 states were my servo compensator. We call that Z. So there's your Kx, there's Kz. To check the linear system, form the dynamics of the closed loop system. That'll be like this. This is feeding back the states, A minus B Kx. Here's the servo, minus B Kz, the servo dynamics. Input with respect to D, input with respect to R. There's a minus sign right there. So doing that, got the minus sign in. Take the step response. Again, MATLAB does not have a step response due to a sine wave input. So I'm going to use the function that we came up with in this class called step 3. There I need to specify the states. The initial condition going to be zeros. My time vector, my disturbance is 1. My reference is sine of 0.5t. Now take the step response with respect to R. So here's the B matrix with respect to R and R. So here's my set point, the sine wave. There's the output. It should track the sine wave. That's what the servo compensator does. It's got a pole at plus minus j.5 radians per second. It should track a 0.5 radian per second sine wave. So that looks good. If I feed it a disturbance, here's the B matrix with respect to D. Here's my constant disturbance. That's just a vector of 1s. It responds and then goes back to 0. Check. It rejects a constant disturbance. And from superposition, if it does each one separately, it does combinations thereof. So now let's go to the nonlinear system. That would be over here. So here what I'm doing, it's got a small font. Okay, there, just increase my font size. I'm going to start out, here's the controller for this semester. Mass is 4 kilograms, the ball is 1 kilogram, length of the beam is 1.3 meters. Starting out at 0, here's the feedback gains that I calculated earlier. Here's my servo compensator. The initial states on the servo are 0. I don't know what else to do. Coming later. Starting out for 30 seconds, my set point is sine of 0.5t. Here's my control law. I'm feeding back minus kz times z minus kx times x. Given u, find the dynamics, find the servo dynamics, integrate x, integrate z, move time forward, and all looks good. The blue line is the observer. The observer we're not using yet, so it's just kind of sitting still. Okay, so that's the first part. That's actually the sea level problem. Can I get this to work if I can measure all the states? Well, at the B level, suppose I can't measure all the states. Suppose I can only measure position and angle. Well, in that case, I need a full order observer. So let's pick a C matrix. I'm going to use position plus 10 times angle. Again, with the pole placement, the algorithm we're using only handles a single input. So I can't handle 2 of them. I would like to use angle. There's information there, but it's not observable from angle. So let's use position plus angle. It could be plus 10, minus 10. I just chose 10. With C, once you pick C, place the observer pole somewhere. I chose 1, 2, 3, 4, and here's the observer gains. Next, form the net system. This is the plant plus the servo plus the observer. So here's the open loop dynamics, here's the plant dynamics, the servo dynamics, the observer dynamics. When I close the feedback loop, I'm going to feed back the observer states, not the plant states, because I can't measure all the plant states. So Kx goes over here. I'm feeding back the observer states. Doing that, this is now 11th order. I've got 4 states for the plant, 3 for the servo, 4 for the observer. There's no constant input at the B level, so this could actually be 2nd order, but I don't want to redesign my controller. So I'm going to design it for 3rd order. Put it all together, you've got your 11th by 11 A matrix, the B matrix with respect to R, the C matrix, I'm going to look at the position and estimated position. Take the step response when the 8th state, which is what? 1, 2, 3, 4, 5, 6, 7, 8. Whatever that is. Slight difference in the 8th state. Take the step response, and the linear system looks good. Here you see the observer is tracking. It converges and tracks. Here's my set point, and the system eventually tracks the set point. That's just using position and angle. Now on the nonlinear simulation, let's go back over here. What I'll do is add the full order observer. So here's the full order observer. There's the C matrix I'm picking. This is kind of arbitrary. Other ways of doing it, that's what I did. Place the poles, find H. Now, instead of feeding back position, let's do that initially. Let's feed back the actual position. That should work, because that's what we did previously. Add in the observer. The observer states tries to track the plant states by feeding back the difference between the actual position and angle and the estimated position and angle. Integrate plant, observer, servo, move forward in time, let her rip. So there, if you notice, the observer, the green guy, was initially wrong, fairly quickly converged. That's what the observer does. The H forces the plants to converge. If I now feed back the observer states, which is really what you want to do, if I knew these states, I wouldn't need the observer. Since I don't know the states, I do need the observer. Feed back the observer states. It's a little bit squirrely initially. That's the observer's converging. Once it converges, then feeding back the observer states is the same as the plant states. The two have converged. Makes no difference which one you use. Okay, that's at the B level. At the A level, I need to modify the system a little bit. So at the B level, I've got the plant, I've got the servo, I've got the observer. There's no constant disturbance, so this isn't there, that isn't there. It should track. If I add a constant disturbance, it will no longer track. To fix that, I need to add a constant to the observer. That models the plant plus the constant disturbance. Once that tracks, I can then feed back the observer states, then track a sine wave, reject a constant, and it should all work together. So that is test number 2. And just a sidelight, a couple people tried doing the A level without this constant term in the observer. You need it. To illustrate that, the simulation that I'm running does not take that into account. My observer is just 4th order. If I add the get rid of the constant disturbance, everything is fine. The plant and the observer converge. Everything's tracking. If instead I add a constant disturbance, here's what happens. So there's the plant, there's the observer. They no longer track. There's a constant hitting the plant that doesn't hit the observer. That goes through the observer gains and causes the observer model to be biased by constant. So it's no longer tracking. The observer actually tracks the set point, because that's my control law. I'm using the observed state. The plant is missing it by a constant. To fix that, I need to add that integrator to the observer. But anyway, that's test number 2 for 463.